A few months ago, while lying in bed one night, a thought flashed through my head: if voice is the future of computing interfaces, what about those who cannot hear or speak? I don't know what exactly triggered this thought. I myself can speak and hear and have no one close to me who is either deaf or mute, nor do I own a voice assistant. Perhaps it was the countless articles popping up on the proliferance of voice assistants, or the competition between large companies to become your voice-activated home assistant of choice, or simply seeing these devices more frequently on the countertops of friends' homes. As the question refused to fade from memory, I knew it was an itch I needed to scratch. It eventually led to this project, a proof of concept where I got an Amazon Echo to respond to sign language, American Sign Language, ASL, to be more precise, since similar to spoken language there are a variety of sign languages as well. Early research. The broader pieces of the system I wanted to put together for this experiment were quite clear in my head early on. The broader pieces of the system I wanted to put together for this experiment were quite clear in my head early on. I knew I needed a neural network to interpret the SIGs, a text-to-speech system to speak the interpreted sign to Alexa, a speech-to-text system to transcribe the response from Alexa for the user. I probably spent the most time early on trying to decide what neural net architecture would be best suited for this. I came up with a few options. Since there is both a visual and temporal aspect to a sign, my gut was to combine a CNN with an RNN where the output of the last convolutional layer, before classification, is fed into an RNN as sequences. The technical term for these I later discovered is long-term recurrent convolutional networks, LRCN. Use a 3D convolutional network where the convolutions would be applied in 3 dimensions, with the first 2 dimensions being the image and the third dimension being time. Instead of training a CNN on individual frames from a video stream, instead train it only on optical flow representations which would represent the pattern of apparent motion between 2 consecutive frames. My thinking with this was that it would encode the motion which would lead to a more general model for sign language. Use a 2-stream CNN where the spatial stream would be a single frame, RGB, and the temporal stream would use the optical flow representation. The approach I finally settled on was entirely different. The TensorFlow.js team has been putting out fun little browser-based experiments both to familiarize people with the concepts of machine learning and also to encourage their use as building blocks for your own projects. For those unfamiliar with it, TensorFlow.js is an open-source library that allows you to define, train and run machine learning models directly in the browser using JavaScript. While they both take an input image from the webcam and output a prediction based on the training data, internally each operates differently. Pacman Webcam, this uses a convolutional neural network, CNN, where it takes an input image from the webcam and passes it through a series of convolutional and max pooling layers. Using this it is able to extract the main features of the image and predict its label based on examples it has been trained on. Since training is an expensive process, it uses a pre-trained model called MobileNet for transfer learning. This model is trained on the 1000 ImageNet classes but optimized to run in browsers and mobile apps. Teachable machine, this uses a KNN, k-nearest neighbors, which is so simple that technically it does not perform any learning at all. It takes an input image from the webcam and classifies it by finding the label of training examples that are closest to this input image using a similarity function or distance metric. However, prior to feeding the KNN, the image is first passed through a small neural network called SqueezeNet. The output from the penultimate layer of this network is then fed into the KNN, which allows you to train your own classes. The benefit of doing it this way, instead of directly feeding raw pixel values from the webcam into the KNN, is that we can use the high-level abstractions that SqueezeNet has already learned, thus training a better classifier. After thoroughly testing the 2 approaches and realizing that both systems performed comparably on my tests, I decided to use the teachable machine as my base since KNNs can actually perform faster/better than CNNs on smaller datasets. They become memory-intensive and performance drops when training with many examples, but since I knew my dataset would be small, this was a non-issue. Since KNNs aren't really learning from examples, they are poor at generalization. Thus, the prediction of a model trained on examples made up entirely of one person will not transfer well to another person. This again was a non-issue for me since I would be both training and testing the model by repeatedly performing the signs myself. Here's a high-level view at how the system works start to end. On launching the site in the browser, the first step is to provide training examples. What this means is using the webcam to capture yourself repeatedly performing each sign. This is relatively quick since holding down a particular capture button continuously captures frames till you release it and tags the captured images with the appropriate label. The system I trained contained 14 words which in various combinations would allow me to create a variety of requests for Alexa. Once training is complete, you enter predict mode. It now uses the input image from a webcam and runs it through the classifier to find its closest neighbors based on the training examples and labels provided in the previous step. I then use the Web Speech API for speech synthesis to speak out the detected label. If the spoken word is Alexa, it causes the nearby echo to awaken and begin listening for a query. Also worth noting, I created an arbitrary sign, right fist up in the air, to denote the word Alexa, since no sign exists for the word in ASL and spelling out Alexa repeatedly would be annoying. Once the entire phrase of signs is completed, I again use the Web Speech API for transcribing the echo's response, which responds to the query clueless to the fact that it came from another machine. The transcribed response is displayed on the right side of the screen for the user to read. Signing the wake word again clears the screen and restarts the process for repeated querying.